Hi there, this is the RPS project. I'm Richard and today I'm going to be looking at the current mirror. Now this is a very simple device. Actually it's two devices. It's two NPN transistors sort of back to back with their base tied together, but one of the transistors controls the current through both of the transistors. It sounds very simple, but actually I've had quite a bit of a taxing time trying to work out exactly why this works. So let's have a look at it on the whiteboard and see if I can get it working on the workbench. So here we have the circuit that I'm actually going to be trying to work from, or trying to make work. It's a very simple circuit, and it is basically the essence of what the current mirror is. Basically two transistors. Now they're connected at the base, so I'm taking it that the control of this is by controlling the base current, because they are after all BJTs, current amplifiers. We've got the collector of, let's say, side 1. I'm going to call this side 1 with T1, and this is side 2, T2. So to me, when I look at this circuit, I'm saying that side 1 is going to be controlling side 2, the left hand controlling the right hand, whichever way you want to look at it. Got resistor up here. Obviously we're going to need that as a voltage dropper, and then the only other thing that's in here really is the transistor itself. Now this is where I've struggled to try and understand what this thing is doing. Why is the current on this side the same as the current over this side? What is happening between these two transistors that makes it able to mirror the current on either side? It looks pretty simple, but yeah, it takes a little bit for me to get my head round what is actually happening there. So let's have a look at it on the workbench. So here's my circuit all set up on the breadboard. I've got my two transistors and an LED and a pot, two multimeters. This one is going to be reading the current on the left transistor, and this one's going to be reading the current on the right transistor. So this is effectively the left hand side, a right hand one that's being controlled. Basically what we're looking at is this. Now I've added a pot in here just so I've got some control when I first turn it on. What I'll do is I'll then turn the pot all the way up. It show that the current is increasing as I reduce the resistance, and then the only thing that I'll have is this resistor, which is, let me get my pen out, is this one, which is actually a 2K2, and there's no resistor on this side at all, just the transistor. And now first of all I'm going to look at with the ammeters. I'm going to put an ammeter in there and an ammeter in there, so that's where I'm going to start from, and I'm going to have a look at the current that's going to flow through both of these transistors as I turn this pot up or down, whichever way you want to look at it. So let's get on with that and have a look at what I get. So I've turned that on. Obviously nothing at the moment because it's because that big 10k pot's there stopping anything from happening. So if I now turn that effectively, I suppose, down, so you get some resistance, the LED has now actually come on very slightly and we're starting to get some current flow. And as you can see, the current is basically about the same through both parts of the circuit. But yeah, I turn that pot further up, further down I suppose, then it does what it's meant to. It mirrors the current. The left hand current is mirroring the right hand, or the right hand current through transistor 2 is mirroring the current through transistor 1. And as I turn it up more, it keeps on going up. Now actually we've got a slight discrepancy now creeping in. You can see that I'm getting more current through the LED than I am through transistor 2 than I am through transistor 1. As I turn this, if I just whack it all the way up, so there's just the 2K2 resistor, you can see that over here I've got 2.7 millivolts. It's going up slightly. Obviously the circuit's not been on, it's just warming up now, so it'll settle, I'm sure it will. But on this side I've only got 2.41 millivolts, so there's less current through this side than there is through the LED. That's a bit odd. You think, why is it doing that? So what I'm going to do is I'm going to have a bit of a deeper dive into this, move the ammeters around in the circuit, and see what else I can discern from this, what's going on and why it's working the way it does. Just have a quick look at the voltages. Now on the transistor 1 we've got a base voltage of about 0.7. You can't really see this, I know, but I'm just doing it as a quick check for myself. But you've also got about 0.7 on the collector, which means on the base of the other transistor I've also got about 0.7, because that's all that's required to turn it on. But on the LED, obviously I've got my supply voltage is 6 volts. Don't worry about the current jumping, because it's just, this has an effect, this 6 volts or 6.2 volts it is, something like that. But across the LED, so that's saying 6 volts, and then on the collector we've got 3.7, 3.6 volts. So 6 volts minus 3.6 volts, that's whatever's left is what this LED is using, and it's also using 2.93 milliamps to turn on. The rest of it's going through the transistor. So I'm just going to move things around a bit and see if I can get some understanding of why it's doing what it is. So I've moved the circuit around now, and this is looking at, well, let's have a quick look at the diagram so I can better explain. Again, this is my basic circuit, but I've now moved the ammeters around, so I've got one here and one here, so I can look at the current going into the collector and the current going into the base of the left hand transistor of T1, T2. I suppose I ought to have said what transistor I'm using. Let's have a quick look so I can find that. It is well it's an odd one. It's out in the bin box. It is a 2N5551, which is actually a high voltage transistor. Not really sure what it's used for, but that's what it is. But yeah, anyway, I've put an ammeter on the collector, ammeter on the base, so I can see what the current is doing on this side, and then what I'll do is I'll have a look at this side. But let's start over here. Right, so let's turn the pot up or down. See, the LED has actually come on, and I've got some current flow already on the collector, but you're not seeing the base, partly because these multimeters just aren't sensitive enough to see that small amount. So let's just turn this pot all the way down so we can see it operating, and there you go. I've got 17 microamps on the base and 2.3 milliamps on the collector. 17 microamps and 2.38 milliamps. So got a note of that now. Put that down so I can see what I've got. And now I'm going to shift over and have a look at what I'm getting over on the other side, on the T2. So I'm just going to shift things around and have a look at what I'm getting. Now I've shifted things around again, so I've changed over to the other side. Basically what I'm doing now is I'm going to be looking at, let me get and do this. I've got an ammeter in there and an ammeter in there. So now I'm looking at the current flowing onto the collector here and onto the base on the T2 side. So let's have a look at that. So what I'm going to do now is turn the pot down and see what we get. LED is starting to come on. Current flow on the collector. Now we're starting to see somewhat on the base. And if I just turn that all the way down, there you go. Now as you can see there's on the base 17 microamps, 17, 18. It does flicker around as the thing warms up, believe me, it is the same on both. And then on the collector, this one is slightly rising. It does settle after a while when I was looking at it originally. I don't know, 2.55, 2 maybe it comes up to about 2.6 milliamps. So let me just make a note of that. Even though it says it's 18, it's got 19. Let's call that 18 microamps. And even though I wrote 17 microamps for the other side, it is the same. It's just obviously spaghetti junction, slight variances in the air, multimeters. But yeah, it is the same, honestly. But on the collector, I've got 2.6. Let's go with 2.64 milliamps. I'm going to put that in. That's what I'm going to go with. And I'm going to treat it that even though there was a slight difference when I measured this side, that the base on there is the same as the current on the base on here. So that is what I've got. Yeah, it seems to be settling down now. I think it's because the circuit's warming up now, and as I've been doing this, it's all been sort of getting a bit settled, whereas when I first turned it on it was all cold. I hadn't had it on till I started recording. So yeah, there are some variances, but yeah, that's shows that bit. So I suppose what I need to do now is have a look at a circuit diagram and find out what all this means, because I've got my measurements. So what does it mean to me? So now that I've done my bit of testing, I suppose if I put some values on here, I might be able to try and understand what it's doing. 18 microamps and 18 microamps, I said there. On this side, onto the collector, I've got 2.38 milliamps, but on this side, onto the collector, I've got 2.64 milliamps. 2K2 resistor. I've got a 6-volt power supply. Yeah, and then I measured it as being, I think it was about 2.4 volts across that LED, which means I've got about 3.6 volts across that transistor. But on this side I've got 0.7 volts, but I've also got 0.7 volts here, or around about that 0.6, 0.7 sort of value, because that's what it takes to turn the transistor on. So when I look at this, I go, okay, well, if I got 6 volts there, that means I've got my, what, 5.3 is it across there? So this is 5.3 volts across that resistor. So in any transistor, usually we determine the current by what I'm going to get across that resistor. So I know I've got 5.3 volts. 5.3 divided by 2200 gives me 2.4, and I've got 2.38, but if you think about it, I've got 18 microamps there. Now I know that's not quite enough, but if I do 2.38 milliamps, let me do it this way, 0.00238 plus the 0.3, then it gives me 2.398. So it's almost the 2.4 that I've calculated coming through that that resistor up there, which is great because that's what I would expect. And the transistor only needs 0.7 volts to turn on this junction, and then it will only draw into the base just what it needs to turn on this junction. That's the way I've always understood transistors. So even though we've got more current here, I'm loading the transistor with more current than it needs, but because this is hardwired to that point, this will just draw just what it needs to turn on. And in this case it's 0.7 volts and 18 microamps, which means by default this side has to be 18 microamps as well. Now when I started this, I had a look at the transistor, which was the 2N5551 NPN transistor, and with the little I did it on the multimeter. Now on the multimeter you get those little testers so you can see what the beta is of your transistors. It's the only thing I've got to check my transistors, but it does seem to work okay. And what I got for mine was 148 as a margin of error there, I expect, but that's my beta, so I can be able to work out what my gain is going to be, my current gain on the transistor. Now looking at this, I've got 2.64 milliamps coming in, but 18 on there, 18 microamps. So, but that's my beta. So looking at this, I go, okay, if I've got 0.123018 times by 148 equals 2.66, and I've got 2.64, so actually that beta isn't far off. My gain is determined by the base current because it's a current amplifier. So yeah, that works perfectly well. That makes sense. This side is determined by the fact that that junction turns on, and the base will draw in just whatever current is needed to make it come on. And with this particular transistor, it's 18 microamps with the restriction that I've put up here with this resistor. So that's what happens. It comes on, and the rest of the current just goes through the transistor because it's turned on. Well, that in effect determines what the base current is on the second transistor, on T2. And that will then determine by its beta value what current will flow through the LED, and that makes perfect sense to me. And of course then you think, well, when I normally turn a transistor on, if I don't have anything in the way here like a resistor, it'll just run away with itself. But it can't, can it? Because if you think about it, this whole side is a bit like just putting a single resistor in front of this transistor and limiting the amount of current that goes onto the base. So it fixes the amount of current coming through. Only instead of using a single resistor, we're using a transistor to set the current level that's going to come onto the base, and determines how much current it will be allowed through the collector emitter junction, because of its beta value. That to me seems very, very simple really. Now that I've actually sat down and looked at it in this format, yeah, that's simple, that's brilliant, that does work. A current mirror. So what you put in here will be reflected over here. Of course, you have to have matched transistors. If you get two different transistors, you're going to get something different out. So, you know, you can buy a matched pair, can't you? You can buy a single IC unit that you plug in that is got two transistors or a transistor array in it, and they're all matched, so they've got the exact same characteristics. But yeah, that did seem to work quite nicely once I got all the figures down. So there you go, the current mirror, a great little device. But what have I learnt? Have I learnt anything? I think I have. I've understood the mechanics of what's going on, why it works, what's happening with it. But what's it for? What's its use? Could I use it for something? Not really sure, to be quite honest. I suppose if you wanted a current to go through a device like I had set up, an LED, but you don't want to have that dropper resistor in front of it, you could use the current mirror, because what current flow through one side is going to flow through the other side. Of course, as long as you match your transistors, that is. But yeah, not quite sure, I suppose. I mean, I see current mirrors in lots of circuits. When you look at an IC device, and I don't know if it's on the 555. I know I like on the little op amp, and you've got your amplifier circuits, LM380 or 386, and other amplifier circuits. If you actually look at the diagrams they give you of how it is on the inside of the IC, there's always a current mirror in there in some sort, somewhere. So I presume it's obviously used quite a lot to help control the circuit and control the current into the rest of the circuit. So yeah, I suppose there must be lots of applications. I've just never really come across them or used them, but the current mirror itself is a great little device. So so yeah, that's the current mirror. I suppose if anybody's got any understanding and suggestions of how that current mirror can be used, what it's doing, then put it in the comments. You know, let me know, because I'd really like to know why the current mirror exists, because it is a nice little circuit, nice little control circuit, I suppose. But that's it really, the current mirror. What else can I say about it? Anyway, if you like this video, give me a thumbs up. If you didn't, you know what to do. Subscribe, and all comments are welcome. See you next time.